In this episode, we are going to talk about capacitors in series. So, in the previous episode, we talked about how to find the equivalent capacitance for parallel arrangement. Here, we are going to talk about series arrangement. So, this is our circuit. This is our voltage source. Let's call it V. And we have our capacitors arranged in series. Why is it in series? Because if a charge is flowing through this circuit, it is going to pass through. The same charge is passing through capacitor 1, the same charge through capacitor 2, and the same charge through capacitor 3. This makes the arrangement a series arrangement. Are we okay? So now let's look at how we will assign the various parameters. So here, let's call this our capacitor 1. So it has a capacitance C1. This too has capacitance C2 and C3. Are we okay? Now, the same charge Q is flowing through the circuit. The same charge Q. So let's note for series arrangement. For series arrangement of capacitors, same charge, which is our Q, flows through them. So if the charge flowing through them is the same, then we will have to calculate for the voltage across each capacitor. So let's look at this. Capacitor 1 is having a voltage V1. Capacitor 2 is also having a voltage V2, and the same thing, capacitor 3 is having voltage V3. Are we okay? Now, we also know that the total voltage in the circuit is V from this voltage source. Are we okay? Meaning the total voltage V is going to be the individual voltages V1 plus V2 plus V3, which is across capacitor 1, 2, and 3. We also know from the equation C equal to charge on voltage, which implies that our voltage is going to be charge on capacitance. Are we okay? So can we also say V1 is going to be, since the same charge is flowing through, it will be the same charge Q over the capacitance C1. Now our V2 is going to be the same charge Q on C2, and V3 is going to be the same charge Q on C3. Let's try to bring this into the equation 1. So our V, let's call this C as the C equivalent. Our V is going to be same charge on the C equivalent, which is the equivalent capacitance, equal to V1. Now V1 is Q on C1 plus V2 Q on C2 plus we have V3, which is Q on C3. When you look at the equation, we have a similar Q. So this is going to be Q on C equivalent equal to, I'll factorize the Q out, leaving 1 on C1 plus 1 on C2 plus 1 on C3. We can also divide both sides by Q such that this Q is going to what? Cancel out. So in all, we are going to have our equation as 1 on C equivalent should be equal to 1 on C1 plus 1 on C2 plus 1 on C3. Are we okay? So this is how we find the equivalent capacitance for series arrangement of capacitors. This is also similar to the parallel arrangement of resistors. So they are opposite to each other. Are we okay? So you can remember one and use the idea to deduce the other. So for n number of capacitors in series, if we have n number of capacitors in series, then the equivalent capacitance 1, on C equivalent is going to be 1 on C1 plus 1 on C2 plus up to 1 on Cn. And it is very simple. Are you okay? So you should know how to use the equation of head and how to also apply them to various arrangements. Are you okay? Now, with this, we can try a question on how to find the equivalent capacitance. Let's look at an example that we have over here. Now, the example. A 3 microfarad and 6 microfarad capacitors are connected in series. A potential difference of 600 volts is applied across the capacitors. Find the charge on each capacitor and potential difference across it. Now let's write down the parameters and start solving. So from the question, we have our first capacitance C1, which is 3 microfarad. So C2 is also giving us 6 microfarad. And we have a potential difference, which is the voltage applied across the capacitors. Let's call it V at 600 volts. So we are to find the charge on each capacitor. Remember, if capacitors are in series, there is same charge flowing through them. So we'll find the Q flowing through all the capacitors. We are also to find the potential difference across each capacitor. So meaning we are going to have a certain V1 and a certain V2. Are you okay? So let's try to produce a diagram of this. We have our voltage source in this form. That will be in series with the capacitors. So here I have my capacitor 1. I will also have capacitor 2 this way. Now this is the voltage V, which is what 600 volts. This is C1, this is C2. Remember the same Q, the charge is flowing through that. I'm going to get a certain V1 and a certain V2 over here. Now, what do we have? Since the total capacitance C equivalent is going to be charged on voltage, from the question, let's find the total capacitance, which is the capacitance equivalent. And let's write this for series arrangement. For series arrangement of capacitors, the equation, let's write that for n number of capacitors, that is going to be 1 on C equivalent will be 1 on capacitor 1 plus 1 on C2 up to the nth capacitance. Are you okay? So fortunate for us, this is just 2 capacitors. We are going to get our 1 on C equivalent to be equal to 1 on 3 micro to the power negative 6 plus 1 on 6 to the power negative 6. So with this, if we are to find C equivalent, then our final answer is going to be 2 microfarad. Are we okay? There's a secret here. Anytime you find the equivalent capacitance for 2 capacitors in series, the answer should be less than any of the capacitance. So here we saw that the capacitance, they are 3 and 6. Since they are connected in series, the total of final equivalent capacitance should be less than 3 and should be less than 6. So we had what? 2 microfarad for the total equivalence or the equivalent capacitance. Are we okay? So with this, we can calculate for the charge. So here from this formula, let's call this equation 1. From equation 1, we can see that our charge is equal to C equivalent multiplying the voltage, which is going to be, we have 2 micro 2 to the power negative 6 times what is the total voltage? That is 600. Meaning for each capacitor, a charge of 1.2 to the power negative 3 coulomb is passing through it. So the charge here is 1.2 to the power negative 3 coulomb. Are we okay? So the second part says we should find the potential difference V1 and V2. As the charge is passing through the capacitors, what is the voltage across each capacitor? So we can see that we will have to apply a new formula where we are going to get our V1 to be equal to Q, which is the same across each of them, over C1. Now for V2, we also have Q, which is the same over C2. So with these two equations, we will be able to calculate the voltages across each capacitor. So let's look at the voltages. V1, that is going to be Q, which is the charge. That is going to be 1.2 to the power negative 3 on what is the capacitance for the first capacitor, which is 3 to the power negative 6. And with this, we are going to get a voltage of 400 volts. There's no need to stress. There are two capacitors. The total voltage is 600. One of them is taking out 400. So meaning the second one will automatically take 200 volts. Are you okay? If it is objective, you can just do it straight away. But for theory, let's also look at if it is true. So V2 is also going to be Q, which is the same charge, 1.2 to the power negative 3 on the capacitance of the second one, which is 6 to the power negative 6. And when you punch this, you are going to get your 200 volts. So you can see that the total voltages is going to give you 600 volts. So thank you for watching this episode. Kindly subscribe to the channel, like the videos, drop your comments, and check out for the next episode, which has 3 solid examples on the arrangement of capacitors. You will need to watch that. See you.